you can have a look at the course outcomes yourself. As I've always been telling you guys, at the end of semester, right? Go through the course outcomes back and make sure that you actually learn all the CO1 to CO4. All right. If I explain this one by one, it won't make sense to you because you have not learned the basics of this course, the applied mechanics course, right? Only at the end of the 14 weeks of this course can you understand what is meant by the course outcome here, right? So go ahead, just take a read on this course outcomes, and at the end of semester go back to this course syllabus and make sure that you take all these four course outcomes, right? All these 12 lectures, I think 12 lectures, yes, 12 lectures eventually is going to be crammed up into these four course outcomes, right? So at the end of the day, this course is to cater for these four course outcomes, all right? So that's it for the course outcomes. And then for the evaluation system and marks distribution. So for this course, we will have two tests and two assignments, right? So each test and assignment will carry a 15% weightage. All right. So test one, test two are both 15%. Assignment one and assignment two are also both 15%. All right. The assignments are all group work. All right. So you have two group works here and then two tests for individual assessment. All right. So your final exam will be at 40% weightage. All right. Any questions for the assessments? Everyone understand this one? Okay. Give a tick if you understand. Anyone? Hello.
Understood.
Understood? All right. So if you can hear me, just give a tick or just say something because all I'm seeing is just blank screen, right? Right. So I can't really see you guys. Okay. Okay. All right. Right. So everyone understand this part. All right. So these are the course schedule for this course. All right. So you can see today is the first week, March 27th. So the topic that we'll be learning is I'm going to be explaining the OBE syllabus, the introduction, and we're going to learn part of chapter 2, which is resultant and resolution of forces. All right. So in here you can see where we will be having our test. So you can see here week 5 we will be having our test 1, which will cover topic 3, topic 2, topic 2, topic 3, and topic 4. All right. So basically test 1 is this one. All right. And then on week 6, we will have our assignment 1, which will cover topic 5 and topic 6. All right. And then so on. For assignment 2, topic 7, 8, 9, this one. And then lastly, for test 2 here, it will cover topic 10, topic 11, and topic 12, which is this one. All right. So each one will cover different course outcomes. This is for course outcome 1, course outcome 4, course outcome 2, 3, and then course outcome 2 and 3 as well. All right. And then we will have our revision week on the 14th week, which is the 3rd of July. Right. So two assignments, which is group work, and then you have two tests. All right. And Raya will be somewhere, I think, it should be somewhere this week, if I'm not mistaken. All right. So for that week, we will have to discuss about class. Do you want a recorded class for this week or for this week, right? But that on later we will discuss with the class representative, right? You should discuss with your class representative first, then let me know how we can cater to your needs, right? Because some of you is in Peninsular Malaysia, so we have to go back and so on. So we have to sort this thing out later after the class. All right. So that's it for the course schedule. All right. So because we are doing online class, right? So for the next 3 weeks, we will be doing online class, right? So for tutorials, we will be doing recorded tutorials, right? So how this work is in the ITEL system, right? I've already posted the link where you can assign yourself to a specific tutorial questions, right? So assign yourself to a tutorial question, and on the following week, I think our tutorials will be on Thursday, right? So on Thursday, to those who have to present on that day, you can submit your recorded video 1 day before the tutorials, right? So you submit your recorded video presentation for that question, submit to me, and I will then check your videos if it's correct or not. But you can check it by yourself, because for every tutorials that I've published in the ITEL, there's an answer that I've given forth, right? There's an answer there. So if you get the answer, you're correct. If you don't, you have to try again until you get the correct answer. All right. Once you submitted the video tutorial 1 day before, on the day of the tutorials, I'm going to publish your video solution, right, on ITEL, so that everyone can learn from that solution, that answer scheme. All right. So there's not going to be any uh, online class like lecture for the tutorials. I'm just going to upload the video solution, the recorded video solution that your friends made, and then you can study by yourself, right? You can try to do the tutorials by yourself, and if you cannot do the tutorials, you can refer to the video solution made by your friends, right? So after this session, I want all of you to go to the ITEL session, to the ITEL website, and then pick a tutorial question for yourself, right? If you do not pick the tutorial questions, I'm going to assign the questions to you myself, right? So to those who have assigned yourself for chapter 2, you're going to have to send the recorded video presentation next week. All right. For this week, there will be no tutorial session because it's just going to be introduction, right? As you can see here, this week is just going to be OBE syllabus and introduction and so on, right? So there's not much tutorial going on. So tutorial will start on week 2. All right. So week 2, we will have tutorial. So this Thursday, we don't have any class. All right. But next Thursday, we will have our tutorial sessions. All right. Everyone clear on that? Everyone clear? Right? Everyone clear on that? Right. All right.
Yes,
Okay.
everyone.
All right. Good. Good. So everyone is clear on that. Okay. What else should I tell you guys? Oh, yeah. The attendance. All right. So the attendance thing is you need to sign your attendance, right? For the 14 weeks that I'm going to be teaching this course, you have to sign your attendance every Monday and Thursday, right? So there's no longer an excuse saying that you forgot to sign the attendance, because as UMS have told me before, class is will always be on Monday and Thursday, so you cannot forget, right? That's what they told me. They're going to they told me that I cannot accept excuses by students that say that they forgot to sign the attendance, because class is consistent. Class will always be on Monday and Thursday, so do not forget, right? Even if for the tutorial session we do not have an online class, we only have like a recorded session of presentation, but I'm still going to post the attendance link on ITEL, right? So you have to sign your attendance every Monday and Thursday, with the exception on this Thursday, because this Thursday we don't have any tutorial read yet, right? But for today, you have to sign your attendance, and then next week, every Monday, every Thursday, you have to sign your attendance, or if you don't, you have to submit a letter of absence to the URL link that I've posted on ITEL. All right. So remember that, always sign your attendance. Okay. And for the tutorial video presentation is only until uh, before Raya, right? So after Raya, we will be having our tutorial session as usual. So you don't have to record any video. You will have to come forward and present your solution during our tutorial sessions, right? So the recorded video presentation is only for the first 3 weeks, right? Because we are doing online classes, right? So tutorial sessions, you can record your solution with sound, all right, or subtitles, whichever way you want, and then you upload it on ITEL, and then I will post it on ITEL later, right? But after Raya, no more video presentation, everyone. To those who assigned yourself to that specific question, you have to come forward and present to the whole class, right? All right, so I think that's it for the OBE syllabus. Okay, so I think we can start on the introduction, right? All right, so can everyone see the slides here? Can everyone see the slides? All right, right. Okay, everyone
And
can
doctor.
see the slide. Okay, good, good, good. So this is lecture 1, which is Introduction to Applied Mechanics. All right. So as you can see here, what is actually applied mechanics? So the definition of applied mechanics is basically in the name itself, right? Applied mechanics. If you divide it into two, you have applied and you have mechanics. So what does applied mean, right? Applied meaning it's practical, it's physical. You are applying something, right? And mechanics is just a system. Imagine like gears or a building. In a building, you have a lot of system, right? You have elevators, you have beams, you have columns, and all that, right? So a building is actually a system. So a system is basically a mechanics. So an applied mechanics is basically the study of how a system react to forces on it, right? When you apply forces to something, we observe what the behavior of the system. We check the behavior of the system, the mechanics, right? So that is applied mechanics. We observe the behavior of system when we apply forces into it. All right. So applied mechanics can be divided into two. The first one is static, and the second one is dynamic. All right. Static, it means that the study of a system is in rest or in uniform motion, right? Static, it's not moving, right? Like buildings. Buildings do not move. So if we are studying the applied mechanics for statics, it means for building, for example, it means that it is not moving or it is in constant uniform motion, right? For example, if it's moving at 2 kilometers per hour constantly, then we regard it as a static as well, right? Then we have a second one, which is dynamic. Dynamic is the study of a system in motion. Means any system or any object that is moving back and forth, we consider that as a study of dynamics. All right. So dynamics can further be subdivided into two, which is kinematics and kinetics. All right. So kinematics is the study of the description of motion, and kinetics is the study of forces causing the motion, right? So in applied mechanics for our 14-week lecture, it's only going to be divided into two. First one is static, an object that does not move. And then the second one is dynamic, objects that are moving, all right? So what are statics and dynamics? So basically there are branches of mechanics, a field that considers how force affects the behavior of system, right? So this flow chart here represents what I have told you, right? This is applied and this is the mechanics part, all right? Applied and mechanics, all right? So what is applied here is forces, right? So force, for example, like the self-weight, the wind load, the earthquake, snow load, there are a lot of forces in the environment, right? If you still remember your civil engineering materials, right? Self-weight, you have lightweight aggregate, you have middleweight aggregate, you have heavyweight aggregates, all that has their own weight, right? So when you use that material for construction, they have varying weight, and that weight causes a force, right? A downward force. Same thing like wind load, earthquake load, snow load, and so on, right? So these are forces that is applied to a system, right? And then this force here is going to be applied to a system. So a system can either be buildings, bridges, dams, road, tunnels, retaining walls, and so on, right? So these forces will be applied on the system, and then the applied mechanics is we study the behavior, right? The effects. Is it the same? Does it rotate? Does it deform? Does it move? And so on, right? For example, earthquake load applied to bridges, right? So we will want to see if the bridge rotate, does it deform, does it move, does it behave the same? Basically observing the behavior of the system, right? Same thing, you have snow load here, you apply on building, you apply on bridges. So you want to observe the behavior of this building and bridges to see how they behave when we apply those forces, all right? So that's about it. All this 14-week lecture that we're going to learn is just to observe a system when we apply forces into it. All right. Of course, when you apply forces to something, it will, of course, react. It will behave. Right. So for statics, it will not move. For dynamic, after we apply the force, it's going to be moving. Right. So force here applied to a system, and then we observe the behavior of the system, right? So this is a static, the study of forces and the effect on a system in rest or uniform motion. So these are example of static system. So this is a bridge, static, a building here is also static, and also a car moving at uniform motion means that the acceleration is zero. It is also considered as statics, right? It's moving, but it's in uniform motion. The acceleration is zero, so we consider it as static as well. All right. And then we have dynamics. So dynamics is something that is moving, right? Because it is moving, we study the system that is in motion, right? So it's moving, so it's considered dynamics, right? So dynamics can be divided into two, kinematics and kinetics, all right? So kinematics is this one. It's concerned with the geometric aspects of motion like displacement, velocity, acceleration, and time, right? So we do not, for kinematics, right? We do not concern ourselves with force. We only want to know the geometric aspect. And what are the geometric aspects? It's velocity, acceleration, time, and displacement. That's all we need to know. We don't want to know about the forces. For example, like the ball here, right? I want to know the velocity when time is equals to zero. So you get the velocity here. What happens when you want to know when time is equals in 2 seconds? So the ball will be here. What's the velocity here, right? So that's all. We want to know the geometric aspects only, not the force, right? For the force, we go into kinetics. Yeah, right? So this one is kinetics. It's concerned with how forces causing the motion, right? So for kinetics, force plays a major role, right? So for example here, if there's just one train pulling the carriageway here, the small force will give a small acceleration. But what happens when we add two trains here pulling one carriageway? Means two force here, right? So we're going to have a bigger acceleration, right? So for kinetics, we concern ourselves with forces, right? But for kinematics, we don't concern ourselves with forces. We just want to know the velocity, the displacement, the acceleration, and time. All right, at specific time, specific acceleration, specific velocity, and specific displacement, right? But for kinetics, we want to check what happens to the system when we add forces into it. What happens when we increase the force? What happens when we decrease the force, right? That is all kinetics, right? So civil engineers design buildings, bridges, and road. So for the study of statics and dynamics, right? We want our system, because we are civil engineers, right? We want our system to not move. We don't want it to move, right? So if we design a building and so on, right? and you have a lot of forces acting onto the building. So our job is to counteract those forces, right? So example, if you have earthquake load, right? You have earthquake load here, here. This is an example, right? You have an earthquake load here, right? So it's your job to make it not move. So how do we make it not move? We have to counter this earthquake load, right? You can counter it by making bigger columns. You have to counter it by making bigger beams, right? Or making the building shorter, for example, only, right? So that's the study of applied mechanics. Once we observe the behavior of the system, as civil engineers, it is our job to counteract those systems so that our object or our building does not move. All right. For example, if you have a building here, right, and once you do your study, there's a wind load here, right? So when we study the applied mechanics, we know that the building is going to behave. The building is going to be moved to the right, right? So as a civil engineers, it is your job to make sure that we can counter these forces here by making bigger columns, bigger beams, and so on, right? But basically, the essence is we don't want our building to move, because if it moves, the design is considered to be failed, right? We don't want our building to move. People don't feel safe in a building that is moving, all right? So this is the case of the City Corp Center Tower, Manhattan. All right, there's a group of civil engineering students. They actually took the plan for the buildings and they started calculating the design of the wind loads. All right, and when they started calculating the design of the wind load, they discovered that the design made by the engineers is actually incorrect. There's some parts of it that is incorrect, right? They calculated the wind load. It was actually 160% increase in the load. So it's actually very, very dangerous, right? It's called the quartering wind. So it was not considered by the engineers in the design stage, right? That's why probably occupants in the building, they can feel slight movement because the forces are not counteracted, right? You can see here there's wind load here going on here, but then they did not do anything to counteract these forces. All right, they only did a little bit, but because of the incorrect calculation, the wind load was actually much higher than what they have anticipated. Right, these are students, right? These are not engineers yet. These are students like you who asked for a plan and calculate the wind loads by themselves because they want to learn. All right. So it doesn't mean that you're a student, you don't know much. You can actually learn by yourself by doing what the students in in Princeton University has been doing. All right. So this is an example of statics and dynamics, right? If you do not make the counteract the forces here, then this building will be a case of dynamics. It will have motion and it will be moving, which is bad, right? For an undergraduate level, we try to make our building or bridges or any system or any object static, right? Means there's an applied force and then you have to counter the forces to make it static, right? So this is an example. If you don't counter the applied forces, yeah, the Millennium Bridge in 2000 wobbled because it is unable to withstand the pedestrian walking randomly. There's moving loads, right? They did not consider the load to be moving, all right? So it falls off, right? Same thing here. Ilford City gates collapse because of insufficient strength provided by the steel connection to withstand the frame self-weight, right? So they did the design of the building, but they did not consider that that material that they are using has their own weight, right? So every material has their own weight, and you have to consider it, all right? If you don't consider it, it will collapse like this one and this one, right? So what can you conclude from the things that I've just told you, right? You can conclude that applied mechanic is very important, right? Because we are observing the behavior of a structure, right? There's going to be an applied forces acting on it. It can either be wind, can be rain, snow, earthquake. It can even be moving loads, right? Moving pedestrians, right? All these applied loads is actually acting on a structure, bridge, building, and so on, right? And when it is applied to a structure, that structure will behave proportionately to that applied force, right? So it will either move forward, back and forth, or it will either collapse, right? Depending on the applied forces, right? So as a civil engineers, it is our duty to observe the behavior. And once we observe the behavior that it's going to collapse or it requires more steel and so on. So we have to counteract those applied forces, right? So that it remains static, all right? So how do we counteract those forces? So when we counteract those forces, we cannot just apply forces just randomly, right? It has to follow certain law. That law is called the Newton's law. Newton's first, second, third, and Newton's law of gravitational forces. All right. So I think this is high school stuff. So I'm just going to skim through it fast, right? I think everyone here knows the Newton's law of motion, right? So basically, the Newton's first law of motion is that objects at rest remain at rest and objects in motion remain in motion unless acted upon by an unbalanced force. So what does it mean? It means that this ball here, if there's no force acting on it, it will remain static, right? It's not going to move, it will remain static. But when you apply forces to it, like kicking it to the left here, it will continue to move. It will move, right? It will now move because you apply forces into it. And it will continue to move, and keep on moving unless there's an external force acting on it, like the net here, right? So when there's an external force here acting on the ball, then the ball will remain static again, right? So that's Newton's first law of motion. It will remain static unless there's a motion or there's applied forces acting on it, right? And then there's this Newton's second law of motion, which is force equals to mass times acceleration, right? It's just telling you if there's mass, when you have mass and you have acceleration, then definitely you will have force, right? For example, like boxing, right? Boxing people have their hands here, right? If they have bigger hands, means bigger mass, right? So the acceleration will be a bit slow, right? But the force will be bigger, right? The same thing if you have smaller hand, the acceleration will be faster, but the force will be slow, right? Basically, it's just explaining this certain part here. Force equals to mass and acceleration, right? And then Newton's third law of motion is every action has an equal and opposite reaction, right? Whenever you apply forces into something, there will be a reaction force applied back to the force, right? For example, the man here is pushing on the wall, and then there's a reaction force pushing back on the man. So brick wall and the man remains static, right? That's when the man is pushing on the wall and then the wall pushes on the man. This is called a reaction force, right? This is Newton's third law of motion, right? For example, the cannon here, when it shoots the cannonball here upwards to the right, right? And then there will be recoil to the left, right? So every force exists in pairs. All right, every force exists in pairs. Imagine when you are sitting down on your chair, right? Your weight goes downwards because of gravity, right? But why do you remain static? It's because there is a reaction force from the chair going upwards, right? So that you remain static when you are sitting down, right? So every forces exists in two pairs. That's what Newton's third law of motion states, right? That every action has an equal and opposite reaction, right? And then there's one more, the Newton's law of universal gravitation. It's basically just telling you about the attractive force that is called gravity, right? So Newton's law of universal gravitation, whenever you have an object going downwards, you have to apply gravity onto it. Okay. Now, this is the same thing. This is the fundamental stuff, the scalar and vector. So Newton's second law, right? So I think everyone here knows, right? Scalar, difference between scalar and vector. So scalar is just a quantity that has magnitude only, right? For example, like time, area, volume, distance, density, viscosity, speed, and so on. They only have magnitude. They do not have direction. So they are scalar quantity. For example, here, there's a motorcycle going to the factory here, right? So if I'm telling the cyclist here to tell him to go to the factory, so the distance between the factory and the house is 120 meter. I do not give direction. I only give the distance, which is the magnitude. So that is a scalar quantity, right? So for vectors, vectors has both magnitude and direction, right? For example, as you can see here, if I'm telling you, okay, I'm going to use this example again. Okay, if I'm telling the cyclist the factory is 120 meters distance to the north, right? So I'm giving the cyclist a direction, right, to the north. So when I give a direction, then it is called a vector. Okay, scalar is only magnitude. Like I'm telling, it's just 120 meter. The distance is 120 meter, right? Just that. So I'm just going magnitude only. So that is a scalar quantity. Whereas for vectors is when I give directions, right? Like 120 meter to the west, to the east, go left, go right, and then straight forward and so on. Those are vector quantities because I'm giving direction plus the magnitude as well, right? Okay. And then this is another important term, static equilibrium, right? Whenever you see this static equilibrium in question, you know that the force will be equals to zero. So what does static equilibrium mean? Static equilibrium is when all the forces acting on a structure is balanced to zero, right? So for example here, this picture on the left is in static equilibrium. This one, right? Because it's not moving. Because you can see here, there's a force pushing to the car using your left hand, but then there's another force pushing the car using the right hand. So the car stays still and it is called a balanced force. Means that car A is in static equilibrium, right? That's the official engineering terms that we use when an object is in static mode, that it is in static equilibrium, right? But if you take the right hand off, as in picture B here, then you will only have one force pushing the car from the left. So this will have an unbalanced force, and then the car will start to move to the right. So this one is not in static equilibrium, right? So therefore, in design, it is important to consider all forces acting on the structure on the system, right? Because in civil engineering, when designing buildings, structures, and so on, right, we want this static equilibrium part, right? We don't want this part, right? So of course, when we study the behavior of the system, it's going to be like this, right? There's going to be wind loads here, earthquake load here, occupants load here, people moving. There's a lot of loads going into the system, right? But then it's our job to make it into static equilibrium. So we have to make a counteracting forces here, 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 and we have to counter all the forces here so that eventually it will become like this one. It will be in static equilibrium. It's not moving, right? So first, we have to observe the behavior of the structure. And once we have observed and we have identified what we need to improve, then we start to add counteracting forces to counter the applied forces acting on the system, right? So this is an example of a building. you have an applied forces here of wind, and then you have earthquake forces here, and then you have weight of the building going downwards because of gravity, right? So this building is not in static equilibrium. Of course, it's going to move, right? The wind forces going to push the buildings to the right. The earthquake forces will shake the building left and right, and then the gravity forces will go downwards and it will crush the lower part of the building, right? This part will eventually crush the lower part because of gravity, right? So once we do our analysis, the behavior of the structure, then we start to make certain changes in the building so that we can counter all the forces that is applied here. So that is applied mechanics, right? How we can counter the wind force? We probably will have to, for example, for illustration purposes only, right? We can make bigger columns here, right, to counter the wind forces. And earthquake force, we can probably install dampers here, earthquake dampers, right, to counter these forces here. And then for the gravity loads here, we can make the top part of the building smaller column, but as it goes down, we make into bigger and bigger columns, right? So that it can sustain the loads from above. All right. So those are the things that you can do and you will do later as you progress your years, right? Because I think in your third year, eventually you will have to design reinforced concrete structures. And if you don't understand your applied mechanics now, which is the behavior of the system, you're going to have a hard time later when designing structures, right? So these are the basics. Polish your basics so that at the end of your study here in UMS, you won't have a problem understanding things that are difficult, right? Understanding things that are difficult, it depends on your knowledge on your basics, right? If your basic is strong, if your applied mechanics is strong, then any problems that you will encounter later during these designing years, during your third or fourth years, you can actually work your way through it, right? If you understand your basics. But if you don't understand your basic, you're just memorizing stuff, memorizing how to calculate this one, memorizing how to calculate that, you're going to have a problem, right? Because not one problem is the same. Every problem is different, right? For example, you have wind forces, but not all wind forces is the same. Some will have quartering wind, like what I just presented. Some will have like normal wind and so on, right? So all that, how you solve that part will depends on your grasp on your basics, right? So if your applied mechanics is good, you've polished it before you progress to your second year, third year, and fourth year, you won't have a problem later in your years, right? But if you are struggling now to understand the applied mechanics part, then you're going to struggle in your following years, right? So it's not hard. This course is not hard, but you just have to pay attention and understand everything, right? If you don't understand, you can just ask me and I will help you understand it. Don't memorize it. Don't memorize the solution on how to calculate certain things, right? If you memorize it, it's not good, because if I just change the question a little bit, then you definitely will get confused, right? Try to understand why that calculation is done that particular way, right? If you understand it, you're going to have no problems later. All right. Now, this is the important part. This is the free body diagram, right? So to analyze forces on a structure, engineers use a free body diagram. So what is a free body diagram? A free body diagram is basically this one. You have a point of application, and then you have a force here, right? This force will show the direction, will show you the magnitude, right? A free body diagram is very important because drawing back all the buildings, all the bridges, all the dams, right? It's going to be very hard to draw it back again, right? So with what you can do is you can simplify the object and make it into a free body diagram so that it's easier for us to do the analysis, right? What I mean by that is this one. This is an example 1.1. Okay. So a block of mass m here is suspended by two ropes as shown in figure 1.1. Draw the free body diagram of the figure, right? So this one is the figure, right? It's a bit hard to analyze it because because there's a block here and there's ropes here, there's slabs here and so on, right? So what you can do to simplify it, you can make it into a free body diagram here. So this is what we call a free body diagram, right? So mass here is this one, mg, mass times gravity to find the weight. And then you have your force here and then another force here, right? So that's a free body diagram. It's just making the picture more simplified so that we can calculate the mathematics more easier, all right? So this is an example, all right? Another example of free body diagram. A pedestrian is crossing a bridge as shown in figure 1.2. Draw the free body diagram of the figure, right? So if we have to analyze this one, it's a bit complicated, right? Because you have a bridge here, you have this soil, this pedestrian here, right? So we can make a free body diagram from this figure here, right? So of course, this is a bridge, right? So when you have a bridge, that bridge has its own self weight. So you will have one force going down here, mg, mass times gravity, right, of that bridge. What else? The pedestrian, right? The pedestrian will also, there'll also be forces going downwards. The weight. So weight is mass times gravity, right? So what else? That's the reaction force here going upwards, right? Right? Remember Newton's third law, every action has a reaction, right? So when you're putting the bridge here, it does not break apart or go down, right? It's static, it's in static equilibrium. And if it's in static equilibrium, meaning there's a reaction force going upward that counteracts these two forces here, right? So it is in static equilibrium, right? This reaction is counteracting this one, this reaction is counteracting this one. Okay, so this is the free body diagram, right? So as you can see here, this one is easier on the eyes, right, as compared to this one. If I put on values here, right, for example, this is 20, this is 30, this is 40, this is 50, right? It's going to be hard for us to analyze the whole system, right? But when we convert it into a free body diagram here, suddenly it becomes easier, right? Now it's very easy to us to see the forces, right? Forces, reaction force going up, and then the weight going down, right? Because the bridge is in static equilibrium, means this force is counteracting this force, and this force is counteracting this force, right? So it is equals to zero, so the whole thing is not moving, right? But if we add more people here, more people here, more people here, then there will be more forces going downwards, right? Then it will no longer be in static equilibrium, means the bridge will break apart and so or collapse and so on, right? So as you can see, R1 and R2 are reactions from the supports of the bridge. R3 is the weight of the pedestrian, and R4 is the self weight of the bridge. Okay. So I think this is the system of units. I think this one you can read by yourself. It's basic. We are going to use SI units. An example of basic units are length, mass, time, combination of unit. When you combine it, you get acceleration, force, and so on, right? So I think this one you must know already as well. Tera is 10 to the power of 12, kilo 10 to the power of 3, and you need to know how to convert from kilo to deci, centi to giga, and so on, right? You have to be careful for the system of units, all right? Be careful for this one, right? A lot of students, they make mistakes because of the unit. So you have, I know it seems simple, but make sure you really understand your units, right? Changing from one unit to another, because if you get confused during a final exam, then everything will be wrong. Okay. So this is an example of how to change the unit, but I think this one you can do by yourself at home, right? Changing from kg per meter square to kilonewton per millimeter square, right? You can uh, refer this one when calculating this example here, right? So this is just a checking for your understanding, right? So I think this one you can do by yourself as well. So you can categorize each quantity as being either a vector or scalar. So 5 meter is what? Vector or scalar? Anyone? 5 meter? Anyone? It is a scalar.
Scalar.
Yes, it is a scalar. If it's 30 meter per second east, there's a direction here. So it is a vector. 5 meter north is a vector. 20 degrees Celsius is a scalar because no direction, only magnitude. 256 byte is a scalar. 4,000 calories scalar. 75 kilogram is a scalar. All right. Whatever that only has magnitude is a scalar quantity. But if it has direction like east, north, and so on, it is a vector, right? So I think this one you can do by yourself as well. It's changing from Newton per centimeter square to kilonewton per meter square, kilogram to kilonewton per meter square, and so on, right? This is just to polish your units, right? Because a lot of students, they make mistakes when changing the units, right? So these are really basic stuff, but you have to know your stuff, right? You have to know that kilo is 10 to the power of 3, mega is 10 to the power of 6. These are the units that I'm not going to be putting on the exam, right? You just have to know as engineers what kilo meant, what deci, what centi meant, right? And how to convert from milli to deci or centi to kilo and so on, right? So that's the introduction part on the applied mechanics, right? It's not that hard, right? It's just observing the behavior of a system, right? So anyone has any questions before we go to our second lecture? Okay. I can give it like a thumbs up if everyone's okay. So I know everyone is still listening. Right. Okay. A lot of people are still listening to me. Good. Good. All right. So that's about it for the introduction part, right? Just introduction. It's just introducing to you what applied mechanics is, what we will be learning throughout our 14-week lecture, right? So all this crammed up into one introduction chapter, right? But there's nothing to it. There's no tutorials for this one. It's just an introduction. All right. So now we go to our first course material, chapter 2, which is the most basic part, which is the resultant and resolution of forces, right? But for today, because this is the first week, we're just going to learn about the resultant force only. Next week, we'll be learning about the resolution of forces, right? So this is the lecture content, session 125. So for today, introduction, resultant force only, right? So we'll be learning until this part only, session 1 and session 2. Okay, so introduction, right? So a force system occurs when there are two or more than two forces acting on a body, right? So for example, if we have a building here, it is called a force system if there's two or more forces acting on the structure or a building, right? If it's two or more, then it is called a force system, right? If it's one, it's not a force system. It is just a force. We call them a force, right? But when you have two force, three force, four forces, five forces, we don't call it forces anymore, right? We call it a force system, right? And there are 5 different types of force system, and they are collinear, coplanar, non-coplanar, concurrent, and non-concurrent forces, right? You don't have to remember this one because the definition is in the name itself, right? For example, collinear forces, the keyword here is linear, right? Collinear. It means that all the forces of the system acts along the same line of action, right? So I have force 1 here, force 2, force 3 here. They are all in the same line of action. They are all linear. They are all linear to each other. When all the forces are linear to each other, we call the force system collinear forces, right? There's 1, 2, 3 force here. So it's called a force system, and they are all linear to each other. So they are what we call collinear forces. Okay, it's in the name itself. So for example, like this one is coplanar forces. The keyword here is planar, which is plane, right? It means that all the forces is in the same plane, right? For example, here, this is the y-x plane, right? So the PQR here, they exist in the X and Y plane only, right? So that's why we call it the coplanar forces. Means that it's easier for us to determine the location of these forces. Like X here, we know the value here, and then Y here, we know the value here. Same thing for Q, we know the value here, we know the value here for Q, right? It's easier for us to know the location of these forces because they all exist in the X and Y plane. And because they exist in the X and Y plane, we call it coplanar forces. Means they all lie in a single plane, right? The keyword here is coplanar, right? And then the third one is non-coplanar forces. Basically, this is just the opposite of coplanar forces, right? For coplanar forces, they all lie on a single plane, but for non-coplanar forces, they do not lie on a single plane, right? So it's a bit difficult for us to know the location of these forces. So usually this happens when we are assessing 3D forces, right? So you can see here, this is 3 dimension. You have Y, you have X, you have Z, right? So they do not, for example, like force P here, the force does not lie on the YZ plane, the ZX plane, or the YX plane. It lies on all XYZ plane. That's why it is a non-coplanar force, right? Same thing like Q. It exists in X, Y, and Z. Same thing like S here. It exists in X, Y, and Z. If this S force here only exists in Y and X, then it is a coplanar system. If this Q here only exists in, for example, here, it exists on Z and X only, then it is a coplanar force. But when an object or a forces here exists in all three plane, X, Y, Z here, then it is called a non-coplanar force. And usually this is a 3D problems, right? The coplanar force is a two-dimension problem, 2D problem, only X and Y, right? This one, 3D problem, X, Y, Z. They do not lie on one plane only. They, they lie on multiple plane. This is plane 1, this is plane 2, and this is plane 3, right? So you have 1, 2, 3. You have more than one plane. Whereas for this one, it's just single plane, right? So it's always in the name itself. You don't have to remember this one, right? For concurrent force, it means that it meets at the common point of concurrency, right? Means that all the force, they meet at a single point, right? So this single point here is where all the forces meet. This is why it's called concurrent force. It meets at the common point of concurrency. All right. And then for non-concurrent force, they do not meet at any common point, right? So you have force 1 here, 2, 3, 4. They are random. They do not meet at any common point. So these are called non-concurrent forces. Okay. So basically, there are two types of force systems in civil engineering. So basically, there are common trends in civil engineering, right? Usually the trend is in coplanar concurrent force system and coplanar non-concurrent force system, right? You can combine the different system together because in the real world, it's not just going to have one system. You have sometimes there's a combination of force system like this one, coplanar and concurrent, or coplanar and non-concurrent, right? So in civil engineering, usually it's just involving these two, coplanar and concurrent and non-concurrent, right? So this is an example of coplanar concurrent force system. Coplanar meaning it lies on a single plane, right? So this one is Y, this one is X, right? So it lies on the X and Y plane, right? That is coplanar. Concurrent meaning that it meets at a concurrent point. So this is your point here. So all the force are meeting at that particular point, right? So concurrent meeting at a certain point. Coplanar means that it is in the Y and X axis plane, right? So you can see here, this is a coplanar concurrent force system. If you analyze the thing from the front here, it's actually 2D, right? And if you want to measure the front side of the bridge here, it's 2D as well, right? See, it's going to be 2D if you analyze it section by section, right? So it's in Y and X plane, right? It's in coplanar. So this is an example of a coplanar non-concurrent force system. Coplanar meaning that it is still on the Y and X axis, but this time the force, they do not meet at any concurrent point, right? They do not meet at any particular point, right? So it's all random here. So these are the two force systems that you are going to encounter for this chapter, right? Coplanar and non-concurrent force system and concurrent force system. Okay. Now we go to the first calculation part for this chapter, which is to calculate the resultant forces in 2 dimension, right? So don't worry, this one is just basic, it's just in 2 dimension. Next week, we're going to learn about the 3 dimension. Sorry, next week is still 2 dimension, but resolution of forces. Next week, we're going to learn about 3 dimension, all right? So the resultant force. So consider two forces, vector P. So vector, you know what vector is, right? Vector has magnitude and direction. So this force here has a magnitude and it's going this part, it's going this direction, right? So this is a vector. So you have two vectors, P and Q, acting on a particle here with direction as shown below. So these vectors can be replaced by one vector that is equal to both P and Q to produce the same effect on the particle. This vector is known as the resultant force, right? So basically, why do we make a resultant force, right? It's because that sometimes when you have a lot of forces acting on a system, it can be a bit confusing, right? For example, you have a building here, right? And then you have forces here, 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 right? These are four forces acting on a system, right? They all have the same magnitude and direction, right? So instead of analyzing each and every force here, there's a lot of forces, right? You can just make a resultant force and just create one big resultant force to the building here. This one is called the resultant force, right? So instead of analyzing a lot of smaller forces, you can calculate the resultant force of all the forces, the smaller forces, and just analyze one forces acting on the building here. You get me? So it's easier, right? It's easier for us. You don't have to calculate all the numerous forces acting on a system. We just have to calculate one forces that represent all the forces that is acting on the building and so on. Okay? So everyone understood that part? Why we calculate the resultant force? Okay? Everyone okay? All right. Okay, good. It's because that instead of having a lot of forces, we can just calculate one force acting on the system, right? So basically, you're just combining all the smaller forces into one big resultant force. And after you got the one big resultant force, you just have one force acting on the system. See, when you just have one force acting on the system with similar magnitude, with similar direction, then it's going to be easy for us to do our analysis on a object or a system, right? So that's why we calculate the resultant force. So that's what we are doing now, for example. So how do we calculate the resultant force? So we have two forces here, P and Q, right? So we can draw ourselves the resultant force, right? You can either use the parallelogram diagram or you can use the triangular diagram, right? So these are the parallelogram diagram, right? So once you have PQ here, you can just draw and make it a parallelogram. And once you make a parallelogram, you can just draw your resultant force here, right? So this one will be your resultant forces, right? That's the first method to make it into a parallelogram, right? So you have two forces here. Just make kind of like a parallelogram, and at this section here, it will be your resultant force. And this resultant force here represents both P and Q in magnitude and in direction, right? So once you have your resultant force here, you no longer need to refer to vector P and Q because you have one resultant force that represent P and Q in magnitude and in direction, right? So that's the first method. It's very easy. Just draw like a square, and at the end of the square there, that part will be your resultant force. The second one is the triangular diagram. It's the same thing. You have your P, you have your Q, so you close the loop. You close the loop, so this yellow red part here will be your resultant force. So resultant force here is equals to P plus Q, right? Same thing here, or you can rearrange it. Q, P here, and your resultant force is P plus Q, right? So that's the triangular diagram. It's up to you. You can make it a square and draw the resultant forces, or you can make like little triangular diagram here and then close the loop, right? So just only two methods to calculate the resultant force: parallelogram diagram and triangular diagram. But what happens when a system is subjected more than two forces, right? So for example, now we have one, two, three forces. So how do you make a square or a triangle from this one, right? So previously you only have two forces, right? When you have two forces, it's easy to make and find the resultant force, right? But what happens when you have three forces? When you have three forces, you can try and do a force polygon, all right? So it's something like this, right? It's up to you. You can rearrange it however way you want, but the the key thing that you need to do is you need to close the loop. You need to close the loop. You cannot have an opening, right? So you can rearrange the forces, for example, like this one here, right? When I rearrange it, P1 going here, P2 going here, P3 going here, and then I'm closing the loop. So your resultant force is from here to here, right? So I'm closing the loop, so you get your resultant force, which is from here to here. Or you can rearrange it like this one, P1 going here, P3 going here, P2 going here, and then you close the loop, resultant force from here to here. Or you can even rearrange it in a more complicated manner, which is not good actually, but can be done. Like this one here, you go here, 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 and then you close the loop. So R will be from here to here, right? So remember, when rearranging the forces, right, you have to close the loop and you have to follow the direction of the forces, right? It has to have flow. For example, like the point of forces here, right? So force 1 going here, force 2 going here, force 3 going here. So your final resultant force is from here to here. So it's closing the loop and there is a flow of forces in the polygon, right? It has to follow the flow because you have to remember the resultant force is actually the combination of P1, P2, and P3. So it has to represent all these three forces here, right? Because R is equals to P1 plus P2 plus P3, right? So it cannot be at at the wrong direction, right? Because if it's in the wrong direction, means that the resultant force no longer represent the three forces here. The point of doing resultant force is because we no longer want to draw these three forces. We only want to have one singular free body diagram forces, which is the R, right? So that's it's easier on the eyes when you analyze the building, right? So in order to calculate the resultant force, you have to rearrange it in a way that it closes the loop and everything flows at the same direction, right? So once the resultant force here has the same magnitude and has the same direction with the three forces here, then the resultant force that you have just drawn is considered valid, right? This has to be equal in magnitude and direction with force 1, force 2, and force 3. So that eventually we can remove this one and just use one resultant force, right? So that's the polygon that you have to draw if there is more than two forces, right? For example, like there's three forces here, or maybe there's five forces there. You have to rearrange it, close the loop, and make sure the direction of the forces are smooth or coherent, right? So that you can draw your resultant force easier, right? But try to make it into simple shapes like this one. But if you make it into complicated shapes like this one, you get confused as well. All right. But it all depends on the direction of the forces and how you arrange it. Okay. So this is the calculation part. So the easy thing first, to how to calculate the resultant of perpendicular forces. So what does it mean? Perpendicular means that it is 90-degree. So your force 1, you have your force 1 here, force 2 here, and then it's 90-degree here. So how do you calculate it? First, you have to draw your resultant force. How to draw the resultant force? You make a square and connect F1 with F2. And then you draw your resultant force, right? So your resultant force, you know the direction will be going to the right, right? Once you have your resultant force, you can take away F1, F2. So now this is your resultant force, right? And this is the direction, the theta, right? So how to calculate the resultant force and the direction, the direction, the theta, is using Pythagoras theorem, right? So it's easy as that. So Pythagoras theorem, F1 square plus F2 square square root, you will get your resultant force. So the direction of the resultant force against horizontal line is tan theta F1 divided by F2. Okay, as simple as that. Okay, so how to calculate this one is using Pythagoras theorem, right? So F1 plus F square, F2 square, square root, you get your resultant force. And then the direction, you know it's going to the right, right? It's going upwards to the right, but you don't know what the direction is, the angle here, the direction. Remember, this is a vector. It has to have direction, which is the angle here. So how do you calculate? Use tan theta, right? Tan theta is what? Opposite over adjacent, right? So calculate the magnitude here, divide by the magnitude here, you will get your angle here, right? So this is how you calculate tan minus 1 F1 divided by 2. All right, a very simple uh, calculation, right? So this is a question, right? So two forces, 60 Newton and 80 Newton acting on A. has direction shown in figure below. Determine the resultant force. So this is your keyword here, resultant force, so R. And angle produced by the resultant force against negative x-axis, right? So he wants to know the resultant force for this one, and he wants to know the angle at negative x-axis. So from here to here, right? He wants to know this part here, and he wants to know the resultant part there. So the first thing that you need to do is what? Anyone? The first thing that you need to do when you encounter a problem in applied mechanics is always to draw the free body diagram, right? It's very important because this is okay, this is a simple figure, but later you will encounter a very difficult picture to evaluate or to do analysis. So it's very important. You have to polish your free body diagram skills, how to simplify this one into a free body diagram so that it is easier for us to do the calculation, right? So the first thing that you need to do is draw the free body diagram, right? So this is your free body diagram. See how simple it is when you simplify it into a free body diagram. You have one force, 80 Newton, and then you have your second force, 60 Newton, right? So once you do the free body diagram, you have to draw your resultant force. And how to draw the resultant force? You use the parallelogram rule, right? So just make a square here, and then make a line from that the point of action to the square. And that part will be your resultant force, right? Once you have resultant force here, you know where your resultant force is, right? Before you calculate your resultant force, you need to know where it is, right? In your free body diagram. That's why you make a square and put the arrow here so that you know, oh, okay, this is the resultant force. So these are the angle that I need to calculate, all right? So to calculate the resultant force is just using Pythagoras theorem. So we know this one is 60, so put in here 60 square, right? We know the magnitude for this one, 80, put in here 80 square, right? So you know your resultant force will be 100 Newton. So this one will be 100 Newton, right? It's easiest as that. Then you have to calculate the direction. Remember, right? We are calculating vectors, forces, right? Forces are vectors. They have magnitude and direction. You cannot just calculate the magnitude. You have to know where the direction is. So you have to calculate the angle for this one. So tan theta is what? So tan is basic maths is opposite over adjacent, right? So tan theta, the opposite is what? Is 80, right? 80 is here. This one is 80. So put 80 here. Adjacent is what? Adjacent is this one, and this one is 60, right? So put in here. So tan theta 80 divided by 60. Finally, you have your angle, which is 53.13 degree, right? So now you know the magnitude and you know the direction, 53.13 degree, right? But then the question wants to find the angle by R against negative x-axis, right? It wants to know this part here. This is 0, right? So this going here is negative x-axis. So it wants to know the angle going to the negative x-axis alpha here. So it's easy, right? This is basic math. So 180 degree minus theta here, which is 53.13, you get 126.87 degree, right? It's basic maths. This is a plane, right? So this is 90 degree. So this one is 180 degree minus this one, you will get your alpha, which is 126.87 degree, right? It's very simple, right? You just have to draw your free body diagram and then draw your resultant force, and then you start to calculate the magnitude and you start to calculate the direction, right? Magnitude and direction, right? It's easy as that. And the magnitude and direction, the formula is very, very simple. It's just Pythagoras theorem, right? 60 square plus 80 square, you have 100 Newton. and then calculate the angle here using basic trigonometry. Tan theta 80 divided by 60 is 53.13 degree, right? And then sometimes they may ask you further questions like this one, calculate the angle to the negative x-axis. So this one is basic trigonometry as well. 180 minus theta, you get 126.87 degree. All right. So I think this is a very easy exercise. All right. So there are other ways to calculate the resultant forces as well. If you cannot solve it using the Pythagoras theorem, you can use the cosine law and you can use the sine law, depending on what magnitude and what angle you have for that particular problem, right? So for cosine law, it's C here is equals to a square plus b square minus 2ab cos c, right? It always takes the angle opposite of it, right? That's to calculate C. What happens when we change it to B? It's the same thing. So if you want to calculate B, so a square plus c square minus 2ac cos beta. You always take the angle across of it. This one, right? This angle is always across of what we are going to find. Okay, same thing if we want to find A here. If you want to find A here, so it's B square plus C square minus 2AC cos alpha, right? So this one will be alpha. So for this part here, you're always going to take the angle across the magnitude that you are going to find. If you want to find A, so cos C here will be this one, right? If you want to find B, the cos will be this one. If you want to find C, the angle will be this one, right? So this one can be interchangeable depending on what magnitude you have at that particular time, right? And then you have sine rule, sine law. It's the same thing. A divided by sine alpha equals to B divided by sine beta, and then C divided by sine C, right? So you can use either one depending on what values you have for that particular problem. If you have all the values for this one here, then use this one. If you have all the values for this one here, then use the sine law. All right, because each problem is different. So usually sometimes you have more values that is more appropriate to use sine law, and sometimes you have more values that is more appropriate to use cosine law. But the thing is, you have to remember these two formula. All right, basically it's just what you want to extract from these two formula is just magnitude and direction. Same thing here. Magnitude and direction. These are the two things that we want to extract. Magnitude, 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 direction, which is the angle. Same thing here, magnitude, magnitude, magnitude. This one is angle, direction, 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 right? Sometimes you have magnitude, this one, direction, this one. You don't have this one, but you have this one. So you use the sine rule to calculate, right? All right. So resultant of forces in 2Ds. So previously we've calculated the resultant of forces for perpendicular, which is 90 degrees, right? So what happens when it is resultant forces of non-perpendicular forces? Means that this is not 90 degree, right? So if it's not 90 degree, then we'll have to use the formula that I've just shown you. You can either use the cosine rule or the sine rule, right? So the Pythagoras theorem is only useful if the forces is perpendicular or 90 degrees. If it's not perpendicular, like this one, it's no longer 90 degrees, then you cannot use Pythagoras theorem to calculate the magnitude. You have to use the cosine rule law or the sine law to calculate the magnitude or direction here, right? So non-perpendicular, if it's not 90 degree, you have to use these two laws here, right? But the basic of it, it's still the same thing, right? You have two forces here, so you have to find the resultant force. So you draw a parallelogram. Once you draw a parallelogram, you cut it out, and this will be your resultant forces, right? Once you have your resultant forces, now we can use the cosine law to calculate the magnitude, the direction, and so on, right? So this is theta, this is r, beta, alpha, and so on. So you can calculate it, right? So what's easier, I think it's easier for me to show you. I'm just going to do two questions, then the other two questions, you try to do it at home, all right? So this is an example of finding resultant forces for non-concurrent, right? Which is, it is not 90 degree, right? So two forces, 20 Newton and 40 Newton, acting on point O. So as shown, find the resultant of the force system and determine the angle provided by resultant force against positive y-axis. Direction shown by the axis in the diagram is positive, right? So you can see this is the figure here. So what should we do first when we encounter a problem like this? Anyone? Hello? Anyone? Anyone know what is the first step to do here? Yes, we have to do the free body diagram. Because without the free body diagram, you will get confused, right? So it's better for you to set your state of mind now in this earlier chapters, that for every figures that you see, for every applied mechanics problem that you see, draw a free body diagram first, right? Because I've seen it in the final exam, students trying to calculate the resultant force and resolution of forces on the picture itself. I tell you, it can get difficult, it can get confusing, right? Better you draw your own system of free body diagram using rulers, so that it's more systematic and it's easier for you to understand it when you have to solve certain problem. This is easy. This is two dimension, right? So you only have two forces. So of maybe you can still analyze it if you look at the diagram here. But later in the following chapters, you will have more forces to to find the resultant forces, right? So it can get a bit confusing. So it's better to set the state of mind, your state of mind now, to draw the free body. Every time you see a problem, you draw a free body diagram that is easier for you to analyze. All right. So the first thing you need to do is draw the free body diagram. So once you draw the free body diagram, it will be something like this, right? So this is 20 Newton, this is 40 Newton, right? Once you draw the free body diagram, the second thing that you need to draw is the resultant force. And how do you draw it? Use the parallelogram, right? You just make a little box here, and then you cut to it. And then the cut line will be your resultant forces. Now you know where your resultant force is here. You cannot calculate without knowing where the resultant force is. You have to physically draw where the resultant force is first before you can calculate the magnitude and direction, right? Once you calculate the resultant force here, you know that direction will be this one, right? Sorry, this one, theta here. This will be your direction of the resultant force. Okay, so therefore you can use the cosine rule to calculate the resultant force, right? So this is your cosine rule. You know your F1, which is 20 Newton, right? Your or maybe your F1, you take the 40 Newton, right? You know your F2, which is 20 Newton. So just put it inside the formula. And then 2 F1, F2, so 2, 40, 20, and cos 70, right? So this 70, right? So how do we find 70 degree here? Right? It's just basic maths. I mean, you have to polish your trigonometry and your maths. This is a parallelogram, right? So what's given is 110 degree here, right? So 110 degree here and 110 degree here. Okay. So a parallelogram is 360 degrees, right? So 360 degree minus 110 degree minus 110 degree, you will have the angle for this one and this one, right? So divide by 2, you have 70 degrees here and 70 degrees here, right? So it's just basic maths, trying to find the angle for this one and this one, right? Because the only angle that is given is 20 and 110 degree here. But once you make it into a parallelogram, you can know the angle for this one, 70 and 70 degree, right? It's 360 minus 110 minus 110, and then the value you divide by 2, and then you get your 70 degrees, right? Once you get your 70 degrees, put it into here, and finally you will have your resultant force, which is 38.1 Newton, right? It's more so on basic maths, right? You just have one formula to calculate the engineering aspects of applied mechanics. The rest is, it all depends on your knowledge in mathematics, right? This is trigonometry, right? Calculating the angle and so on to get 70 degree, all right? And then to calculate theta here, you can use the sinus formula, the sine formula, right? So 20 divided by sine theta is equals to R. Remember, for sine formula, you always take the angle across of it, right? So R divided by sine 70 degree. So you know what R is. So just calculate this one, and finally you have your theta, which is 29.5 degree, right? So it's easy as that. You just use the sine formula and just substitute all the values inside of the sine formula, right? And then you have to calculate angle alpha here. Is the angle that is made by the resultant force R against positive y-axis. Therefore, alpha is 90 degree minus 20 degree minus theta, and finally you have 40.5 degree. This is basic maths, right? Okay, because as you can see here, x and y here, this is 90 degree, right? So 90 minus 20 minus theta, right? Because why theta here? Because if you still remember your trigonometry, this is actually a z, right? This is a z. So theta here will be equals to theta here. So it's the same thing. So that's why 90 minus this one minus theta, which is this one, right? Then you get your alpha, which is 40.5 degree, right? So these things you just have to really do a lot of practice, right? So I want you to go back at home and try to do question 3 and question 4 and question 5, all right? And then next week we will learn about the resolution of forces in 2D space, right? So make sure you really understand about the resultant of force, right? So go back home and try to do the questions, right? The engineering part is just the formula, right? Mostly for this one, it's non-concurrent. It's no longer no longer sorry, this is non-perpendicular. No longer do we have a perpendicular example, because for perpendicular it's very simple, right? You just use Pythagoras theorem and then you calculate the direction using basic trigonometry. But the problem here is when it's non-perpendicular, then you have to use the cosine rule and sine rule, okay? But in order to effectively use the cosine and sine rule, you have to know your maths well. You have to know how to use the z rule here. You have to know how to calculate the angle. For example, like this one, probably it's z something like this is some connection with that one. So you have to be good at drawing the free body diagram. Like this one, it's complicated, but once it's simplified into free body diagram like this one, it's easier for us to calculate the angle. It's easier for us to calculate the magnitude, and it's very hard for us to get confused because everything is systematic and clear, right? Try to make a neat and clean free body diagram using a ruler, right? So that it becomes a habit, so that it's easier for you to calculate the angles and so on, right? For this example, the only difficulty is calculating the angles, right? Because for the formula part, it's already given, right? The formula is already there, cosine or sine rule. Which formula to use? It depends on which values you have at this particular free body diagram. If you have sufficient values to use sine rule, use sine rule. If you have sufficient values to use cosine rule, use cosine rule, right? The formula is already there. The only hard part is to calculate the angle here. But that one, you have to polish your mathematics, right? Because it's just basic trigonometry. If you forgot, you have to look up in YouTube how to solve trigonometry problems and so on, right? Because those are basic problems, okay? So I think that's the end for our lecture today. So anyone has any questions for today's lecture? Anyone? Everyone okay? Everyone okay? Can everyone do like hands up thing? Everyone okay. All right. So, okay, good. So I think everyone okay. So I think that's the first lecture of the semester. So it's nothing much. It's just calculate. And I know I've said a lot about the introduction part, but the introduction part is just basically introduction you through the whole applied mechanics, just a big picture of things. The real calculation part is this one, the lecture two, and it's just calculating resultant force, right? Using cosine and sine rule. So go back, please do example 4, 5, 6 on your own, because if you don't, you're going to get confused later when we do the resolution of forces, right? Resultant is combining multiple forces into one. Resolution of forces is you have one forces, but you want to break it apart into multiple forces, right? So make sure you understand the resultant force first, combining everything into one resultant force. So this week we don't have any tutorials because we haven't finished this chapter yet. So on Thursday, try to do example 456. If you don't understand, you can just contact me and I will help you understand that example. All right. So this week, no tutorials, but next week we will start our recorded video tutorial. All right. So at the end of this lecture, please go to ITEL and pick your assigned tutorial. All right. So everyone, there's I think 50 plus of you. So just pick any question for tutorials that you want to present. All right. For the first two chapters, I think it's going to be a recorded video presentation, but the rest after that, it's going to be physical presentation, right? So if you don't fill it by this week, I will assign the tutorial question automatically to you. All right. So I think attendance, yeah. So don't forget to sign the attendance. It's very important. All right. uh Okay, so this is the attendance. Okay, so I think that's the end of our lecture. I will see you guys next week on Tuesday. All right. All right. Bye, guys. Okay. All right. Bye. Happy Bubuka
Thank
for
you.
the Muslim. Right.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Bye bye. Okay. Bye, guys. Bye.